Okay, well, welcome to week 9. This is also the week your assignment is due. So understandably, we are not expecting a lot of students turning up in the in-person lecture. But anyway, this will be recorded, so this is your opportunity to ask any questions that you want if you are attending in person. So it gets recorded and you can listen to it later. Okay, so in week 9, we are on a schedule, so that's the first thing. So that's the great news. We are going according to our plan, and we are left with only one layer, okay? Data link layer. So let me draw the stack again, the layer. So that's the application layer, which is sitting on top of transport layer. And then we finished network layer. And now we are in data link layer. Okay. Data link layer. And this is the physical layer, which is out of scope. We are not going to study this in this course. We have finished application, transport, network, and today we are going to start data link layer. We have 2 weeks for this, but you know, in the last week, we try to recap all the lectures, go through some information about the final exam, possibly, talk about the sample of the final exam and things like that. So we need some time in the final lecture. Also, we want to cover wireless and mobile in the data link layer, because this is the norm now. Everybody is using mobile devices like yourself. So you need to understand how the wireless works. But today we will be, this week, week 9, we'll focus only on the wired connection. So that will give us some time to cover the wireless aspects of data link layer in week 10. So we are on a schedule. In week 9, we don't need to cover wireless, but we want to cover these 4 topics. So error detection and correction is something that I already told you several times, that this is done in multiple layers, transport layer, network layer, and now we are in data link layer. So we want to see how the error detection and correction is done in the data link layer. This is a bit different than the way it's done in the transport and network layer. And medium access control is also very important topic in data link layer. So today we'll try to cover the basics of medium access control, the motivation, the taxonomy, and some basic features of medium access control, with some examples of Ethernet. But Ethernet is something that is basically an example of medium access control. Okay. But some details of Ethernet will be covered on Thursday. So if I can cover this on Monday, today, then we should be happy, right? So that's the plan for today's lecture. I just wanted to remind you that usually in week 9, our university starts to collect the surveys, the student rating of the courses that we deliver, with the objective of refining and adjusting some of the problems our students are facing for the next delivery. And this is done by collecting details anonymously. So we never know who is saying what. But then we collect it, and then we spend a lot of time analyzing what you are saying. And then in the next delivery, we tell you how we are adjusting. This course has been running for a long time. We've been collecting lots of things, but every year we still find that there are some areas where we can still offer some improvement. So I really plead you to complete your My Experience survey. This shouldn't take you very long, but the written comments are really important. But we also want your multiple choice rating as well. But I'm not sure if it's already up. But usually in week 9, you have to go to Moodle. And if you go to Moodle, then you should be able to complete it. Or you can also go directly to My Experience and log in. And if you are enrolled student, you should be able to give your voice. Okay, with that, I would like to move into data link layer. And the first thing I want to say that this is about the subnet. So we have studied network layer, and we said that the network layer is about having a router between two subnets, right? So you interconnect two subnets. So machines connected in one subnet can transmit data to hosts in another subnet through the router. The router is a layer 3 device, okay? So all these distance vector routing, link state routing you have seen, these algorithms are for layer 3 network layer. What we are doing today is we are going inside the subnet, right? And just looking inside the subnet, what sort of networking technologies are needed to get a subnet going. Forget about sending a packet outside the subnet. Just think inside the subnet, what technologies are needed, right? So that's the data link layer, right? So that's the first thing. So in the picture, what you see is a subnet. And this is a layer 3 router which is connecting this subnet. So this is the subnet I've been telling you about. So this is our subnet. And this subnet is connected to other subnets and other networks in the internet through a router, which is a layer 3 device. But today we will focus in here, and here you can see a lot of hosts are connected to the subnets, but we also have some devices, right? What are these devices? These devices are not network layer 3 devices. These are called layer 2 devices, data link layer devices. They do not have the distance vector routing or link state routing intelligence. They cannot do forwarding or routing based on the IP destination address. They work below IP, okay? So that's the data link layer, and we have technology in that layer as well, which we are focusing on today. So these, if you have curiosity, what are they called? So they are called switches. Okay. Later you'll see, these are not called routers, they are called switches. Although, for a layman, you know, if you ask them, they might think, oh, switches, routers, and switches, they are similar thing. But explicitly, we are going to make a difference between them today in this lecture and in this course, right? So we'll say switches are layer 2 devices, routers are layer 3 devices. So I'm just going to write it down here so that you don't forget. So layer 3, and these are layer 2 devices. Okay. So they do not have the intelligence to interpret the headers of the IP packet. That's the important thing. So we are going to see these links, how these links operate. These links can be wireless or wired. So they need technology so that many devices can use the same link, for example, through a switch to go from one switch to the other switch, and all the hosts can communicate with each other within the subnet. Right. So the first thing is error detection and correction, right? So you may wonder why again. So if you recall, I'm just refreshing our memories. In TCP and IP, we talked about checksum, right? If you recall, it's one's complement. We just added the 16 bits together, and then we say this is the checksum. And if any bit is in error, then this checksum will be incorrect at the receiver when they compute, and then they can detect the error, and then they can drop the packet. And if it's a reliable transport protocol such as TCP, then an acknowledgement will be missing, and then it will retransmit, so you can recover from such errors, right? But error detection is done through a very simple checksum, right? Both TCP and IP, we said that they use identical technology, identical technique to detect the checksum, to detect the error. That's called checksum, right? Now, in every layer uses is error detection and correction, because they would like to detect error in that layer itself, so that this error doesn't propagate into the other layers and then prolong the error recovery process in the system. So if you can detect it early in your layer and get rid of it, or even correct it, then the other layers are not affected. And as a result, your end-to-end performance in computer networking is improved, right? So that's the overall goal of having error detection and correction at every layer, because this is a question that comes to your mind when we always talk about error detection and correction in week 9, week 8, week 7. Today, one thing I can tell you, that the error detection and correction that you are going to see in the next few minutes will be different than checksum. So it's not the same thing. If it was same, then I wouldn't spend time here. I would just tell you it's the same checksum, but it's not. It's a bit different. And that's why we are going to spend some time. And you'll see that there are two different methods of doing these error detection and correction. By the way, one of the things, if you are wondering, the data link layer, I might have said it in the first lecture, but this is a good time to recall that, is that all the other layers, such as application, transport, network layer, they are all implemented in software. So application is in the application area, application developer area, and the others are in the kernel of the operating system. But they are like the software. But when it comes to data link layer and physical layer, then you will see that they are implemented in the hardware, in the network interface card or the chip, Wi-Fi chip that you have in your devices. And then the desktops, you have some cards. But these days they are going for chips, small form factor. But that's a hardware. So they put a lot of things into hardware for fast processing, because that's the lowest layer, physical layer. When it comes to data link layer, most of it is in the hardware also, but a little bit of it is in software. Okay? Because you're a computer science student, you like to understand what is in hardware and software. So this is a good time to discuss this. So the part that is in software is called driver, and every network interface card, Ethernet, Wi-Fi, they come with this driver, and you have access to this driver through the operating system, because operating system has control over this driver. And for our research, like the students who come to do research with us, then we play with this driver to see if we change the protocol, for example, how would it perform? And then we can go to the driver and we can change the behavior of these technologies for experimental purposes, for research purposes, right? So that's this picture, in case you were wondering what are these slides. So that was a slight detour. I'm coming back to error detection and correction. And I just want to say that there are two different techniques. One is parity checking, and other one is CRC. So today we are just going to discuss two different methods of error detection and correction: parity and CRC, cyclic redundancy check. They operate differently, they behave differently, they detect different kind of bit errors, right? So the first one, we'll start with parity. Have you heard of this parity check before in your life, in undergraduate or in high school? Anyone used it or heard of it, parity? No one? I thought in high school they do teach parity for something, but anyway, it looks like it's a very specific to computer science and digital communication. All right. Okay, so no problem. You don't have to hear about it. Today we are going to understand. But the parity is a very simple concept, okay? It's an extremely simple concept. You just count the number of ones in your stream, right? Everything is binary, 0 or 1. You just count the number of ones in your stream. And you try to make it an even number of ones or an odd number of ones in your stream when you are transmitting data, right? So at the other end, you can again count the number of ones and then see if it is even or odd, whatever parity you have decided. So you have to, if you are using parity, the first thing you have to decide, do I want even parity or I want odd parity? That's the decision you have to choose. There's no difference between them, right? You just need to make a decision. In this particular slide, we are showing you even parity. So I will explain what is even parity with a very simple example which you can see on the slide. For example, you have 5 bits to transmit, 1, 0, 1, 0, and 1. But if you count the number of ones, how many ones do you have in your data? That's your data. If you have this data, how many ones do you have? 3. Yes, I can see your hand with 3 fingers. 3. So if you are interested in even parity, when you are sending this data, we are going to use a single bit parity, for example, right? Single bit. Let's say that you are allowed to add 1 bit only to the data that you are sending. That's the single bit that you can add. Now, let's say that we are going to use even parity. So included this extra bit, the total number of ones in the stream of bits that you are now sending, the data plus the single bit parity should be even. So 3 is not even, 3 is odd, right? So the bit that you transmit as a parity should be 1 or 0? 1. Because if you make it 1, then it will be 3 plus 1, 4 ones in your transmitted bit stream, which is even, right? You want to make it even. You have a control. You have 1 bit in control in your hand, which you can choose 0 or 1. You can't change the data bits, right? Data bits is something you have to transmit. This is a control bit. So you can either make it 0 or 1. So if you are interested in even in this example, because you have just 3 here plus 1, you have 4, and 4 is even, right? How about here? If you want to send these 5 bits, how many bits you have? How many ones you have here? 4. So this has to be 0, because 4 plus 0 is 4. You have 4, even. You want even. How about here? You have 3 plus 1. 4. 4 is even. Good. So everything is even. So that's called even parity. So if you are using single bit parity, right, then in the data you count the number of ones and you decide whether you 1 or 0. So at the end you have total number of ones even. That's simple, right? And how do we detect errors? When we receive the bit stream, we count the number of ones in the data and in this parity bit, all of this transmitted bits, right? And if it is not even, then we have a problem. If it is even, we say no problem, right? This is how we detect a single bit error. So that's the single bit parity. So before we go to two-dimensional parity system, I have a question for you, very quick question. So single bit parity I'm using, right? Does it mean that it will be able to detect all the errors? Someone is nodding very vigorously. So why you are saying you cannot detect all the errors?
There may be several bits that are transmitted wrong.
Okay, so can you give me an example in here that the error pattern will not be detected by this single bit? But can you just give me, just one example?
So if 2 bits is transmitted wrong, it will still be even, but
Okay, so let's say this bit is in error, right? So this 0 was flipped as 1, and you say 2 bits, right? So let's say this bit is in error, so this was flipped to 0, right? Now if you count them, 1, so now it is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1, 10. So still even. There were 2 bits in error, but the parity has not changed, right? It's still even. So at the receiver, you think everything is fine, right? It means that 2-bit errors cannot be detected by a single bit parity system, right? Another question, right? So these are not in the slides, but this is our opportunity. How about 3-bit errors? If 3 bits are flipped in the transmission, including the parity bit, will I be able to detect that 3-bit error, no matter which 3 bits are in error? Can I detect the error using a single bit parity? Yes or no? I didn't hear. Yes or no? Yes? Yes? Anyone with no? Everyone agrees? All 3 bits errors, any 3-bit errors can be detected? Most of you are undecided. Yeah, question.
What if 2 of the 0 bits flip to 1 and the parity bit flips to 0?
Yeah, so there are 3 bits. Someone is giving an example. Okay, let's go through this example and we will find out. Okay, let's say this is our example. I'm using 5-bit. I'm using even parity. 1, 2, 3. So what should be the parity bit? 1. So I make it even. Now you are saying that 2 0 bits are flipped to 1, right? Okay, so I have 2 0 bit. I flip it to 1. Flip it to 1. And you said 1 bit is flipped to 0, right? Okay, I'll flip it to 0. Now let's count the 1. 1, 2, 3, 4, right? And then 5. So at the receiving end, your parity is not even. You sent an even parity, but when you count the number of ones, it's not even. So you'll detect it.
But what if the parity bit flips to 0?
Okay, good. So this is one example. The other example, you are saying this will be flipped to 0, and another one will be flipped to 0, and this 0 will be flipped to 1, right? So count 1, 2, 3, 3 ones, which is not even. So it will be detected. Can you find a combination of 3 bits that will not be detected by this parity, single bit parity? Can you find one? Do I need to find one? Or I can use some common logic to quickly answer this question? If you are using even parity, then if an even number of bits are flipped, I will not be able to detect it. If I am using odd parity, an odd number of bits are flipped, I will not be able to detect the problem. If I am using an even parity, and if an odd number of bits are flipped, I will be able to detect it. If I am using odd parity, and an even number of bits are flipped, I will be able to detect it, right? That's the logic. I don't need to find exhaustive search to find a combination to see whether I can detect it or not. That's the common logic, right? That's what odd and even means. Is that right? Is the logic clear? So that's the power, that's the mathematical explanation of the benefit of a single bit parity, right? So it will be able to detect not only a single bit error, right? It will be able to detect multiple bit errors as well, right? Not all multiple bit errors, subset of the multiple bit errors. Any questions? I see some blank faces, still not sure. But if you have any questions, I can explain. Okay, so before we go to the two dimension, do you have any questions on the single dimension parity system, even parity or odd parity?
So do you like combine even parity and odd parity so that we can like detect any sort of...
If you are using single bit parity system, you cannot combine them. You have to make a decision that this single bit will be used for even parity or odd parity. You don't have any choice, right? You just have one bit.
What if I use 2 bits as the...
Yeah, so that's a good question. So in error detection and correction, when you design, you have to make a decision how much redundancy I want in my system. So single bit means I will just have a redundancy of 1 extra bit that I will transmit on top of the data, right? And it has certain limitations and certain benefits. So that's what we are discussing. In general, as you add more extra bits, as you can allow more overheads in your system, it has better performance in terms of detection and correction, right? But that's a trade-off, right? For every 5 bits, if I send 1 bit, the overhead is 20%, right? If every 8 bits, if you send 2 extra bits, 25% overhead. So that reduces your usable data rate of the system because you're not sending useful bits. Okay, so is that clear how odd parity can detect not only a single bit error, but 3-bit errors, 5-bit errors, 7-bit errors, and things like that, right? Sorry, the even parity. Right? Even parity can detect all the odd. And the odd parity, the opposite. Right? Is it opposite? Or is it still the same? Yeah, it's still the same. It's still the same, sorry. So whether you use odd parity or even parity, so if you change, okay, so we were in even, and we have just seen that if you change 3 bits, no matter which 3 bits you change, you can still detect it, right? What if you are using odd parity? So let's say I want to use odd parity, right? Because odd parity is not here in the slide, so we are going to discuss. If I want to use odd parity, what will be the bit here? Extra bit? 0. Because it's already odd, right? Now, if there is a single bit error, it will be detected because it will flip from odd to even, right? But if there's 2-bit errors, it will go back to odd parity, right? But if you have 3-bit errors, then again, it will change the parity, right? So the correction I'm saying, whether you are using odd parity or even parity, you will be able to detect single bit errors, 3-bit errors, 5-bit errors, 7-bit errors, and odd number of bit errors can be detected. Because an odd number of bit errors will switch the parity, right? An even number of bit errors will not switch the parity, right? So if it doesn't switch the parity, then you will not be able to detect it. But if it switches the parity, you will be able to detect it. So we can detect a single bit error, 3-bit error, 5-bit error, 7-bit errors, but we will not be able to detect 2-bit errors, 4-bit errors, 6-bit errors. We will not be able to detect them with a single bit parity system. Right? Okay, is that clear? Yeah, so now I think this is more robust, our conclusion. That's good. That's single parity. What I'm going to show you at the right-hand side of this slide is called a 2-dimensional parity bit. It's not just 2 extra bit, it's 2-dimensional, okay? So what I mean by 2-dimensional parity bit. So when you are sending data, the data can be lots of bits, right? You might have 1,000 byte packets. We talked about these things, right? 1,000 byte. What does it mean? It means 8,000 bits. So if you just want to use a single bit parity for all these 8,000 bits, you are sending a single bit. Now this is a bit weak, right? What we are doing here is 2-dimensional. So we are stacking all these bits into a matrix, right? Into a matrix. So how do we do the matrix? So you can see an example here. So for example, it can be an 8-bit row, and it can be, 8-bit column. Okay, so here the J number of columns, and you have I number of rows, right? So you can take 1 byte at a time, and then J is equal to, if it's 1 byte at a time you are stacking, then J would be equal to what? 8. And if you have 10 bytes, I would be equal to 10, right? So you can see how easy it is to create a matrix of my data, right? So instead of considering the data as a 1-dimensional stream, you can stack it 1 byte at a time if you want, or 1 word, like 4 bytes at a time, into a matrix, right? So if your data is multiple of 8 bytes, it's very easy to stack them. Okay, now I created a matrix. How do I use the parity system, 2-dimensional parity system? It's easy. For every row, so let's first you decide on the parity you want to use, even or odd. So in this slide, everything is even. But you can switch it to odd if you want. Every row, you have 1 bit. Every column, you have 1 bit. So in this system, you have at least I times j overhead, I times j bits, right? What's this doing? So you can see this row, you will have a single bit parity, right? For this row, you have a single bit parity. And then for every column, you have a single bit parity. So if you take this, and if you take this, then you have I times j parity bits. But what is this? This is another bit. What is this doing? It's a parity bit, right, for these parities. Right? Now, it turns out that this single bit you can either, this bit you can take it either as a column, row or column. For example, these bits are actually parity bits, right? So this is a row of parity bits, and you can create or calculate another parity bit for this row, for example, right? And you can attach an extra parity bit, which is a parity for the parity bits. Okay? So I have one extra bit. So if you want, you can send one extra bit here. So this is the extra bit. Okay? And you can add them, all the rows, and put some number. Okay. So what does it mean? It means that you are sending I times j plus 1. So lots of extra bits. And what can it do for me? I think the slides don't tell you things, but yeah, I can just tell you that if there is any error if there is a single bit error, I think we have a slide. Okay, just the CRC, I don't want to go there. There is no slide, I'll just explain it. Okay. I can use this one. This one. This is the one I was thinking of. Good. We already have it in this slide. So let's say there is a single bit error. Okay, the red one. So this 0 is flipped to 1. Okay, single bit error in my data. If this is the case, this parity bit will be in error. This row, at the receiver, you are computing parity for every row, and you are computing parity for every column, right? So for this row, your parity will be in error, because one bit flipped for this row. Similarly, you will see that the computation, the parity computation for this column will also be in error, because one bit in this column has changed. So the benefit is that you will not be just detecting the error, you will be able to correct the error, right? So this is a powerful thing, because now, so far, what we have studied in transport layer and the network layer is you just detect the error, right? And you just drop the packet. Correction comes from timer retransmissions from the upper layer. But at the data link layer, if you are using two-dimensional parity, the data link layer itself can detect the error and repair it immediately right in the data link layer, so that this is not visible at the network layer. Network layer, when they do the check, they find that everything is fine because it was repaired. So this is a powerful thing, error correction. This is called forward error correction. That is, no backward retransmission is required to correct the error. You are detecting and correcting. So this is the first example, I think, in this course that you have seen, that you not only able to detect, but somehow you can correct it. And this is possible because of the two-dimension, because if you see, if another bit was in error, not this bit, then other rows and columns would be in error. So when this specific row and specific column is in error, you know which bit is in error. So just correct it, right? Is that clear? So error detection and correction. So for the first time we are talking about error detection and forward, this is also called forward error correction. But this is only possible for single bit, right? So can we correct 2-bit errors, for example? Can we detect 2-bit errors? Yes or no? With this 2-dimensional system, can we detect 2-bit errors? Yes? Everyone? Yes? Yes, the answer is yes. Because if there's 2-bit errors, for example, this bit, and let's say this bit is also in error, then this row will be in error, this row will be in error, this column will be in error, this column will be in error. So many errors you are finding in your system, you should be able to say that there is a problem in my data, right? So 2-bit errors can be detected. No matter where you put them, okay, so let's say I'm going to put both of these bits in the same row, okay? So I'm saying this is in error, this is in error, right? 2 bits in the same row. So this row will not be able to detect it. Remember, even number of flipping cannot be detected by a single bit parity. So that row parity will not be able to detect it. But 2 columns will be in error. So you will again detect the problem. So this is more powerful than the single bit parity in 2 different ways. First, it can detect these even number of bit errors. Before, remember, in single bit, we cannot detect even number of bits errors, only odd. But now we can detect them. Second, which is more powerful, more significant, is that you can correct a single bit error. Correction right here, forward error correction, is very powerful because it saves a lot of inefficiencies in your system. So this data doesn't need to travel all the way and then get dropped. Then the timer needs to expire in TCP and retransmission has to happen. You see, so much inefficiencies to recover from a single bit error in the system. But if you can repair it right there, it's very powerful. And that's why it's worth spending a lot of overhead. So there's a trade-off between overhead. To correct a single bit error, you can see so many bits we have to transmit. All these rows and columns, I times j. Okay? Question?
I have a question. So when you're trying to detect and correct a single bit error, would it mean that the parity error for the row and parity error for the column would intersect?
What do you mean by intersect?
So for example, like that 0 there, the parity error and the parity error for the row and the parity error for the column.
Yeah.
It's been
Intersect.
That's
Yeah.
how we know that
Yeah. Okay. Yeah. So good question. Intersect. So this is visual, right? So visually, I'm just showing you it intersect. What it means that for every single bit error, there is a specific combination of row and column that will be in error. That's all it means. Right? So, for example, if you take this bit in error, then is row number 1 and column number 1 will be in error. If you take this bit in error, it will be row number 1 and column number 4 is in error. See, I times j. So you have combinations. So every bit will have a specific combination of row and column that will be in error. That's why you can correct it. That's the intersection visually, looking at that intersection visually.
So once you identify the row and column for that particular wrong bit, that's when you can easily detect it and correct the single
Correct the
error.
bit, yep. Another question.
So, if you will remember as a parity of row I, column j is 0, 1, row I plus 1, column j is maybe 0, 0, something. Is that correct?
What is the question?
Like, just want to validate my understand that for if you remember for the row I, column j check is 0, 1 or something like that. Is that correct? Because like column parity is 0, row parity is 1, something like that.
So what is your question?
Just
I'm just trying to understand your question.
Just want to see in terms of the system that how it's like how you say it's all the combination.
Oh, how the combinations. Okay, so the question is why there is a specific combination of rho and j. So for example, let's say that this bit is in error, okay? Okay, if this bit is in error, which row will be in error? Row 1, right? The first row will be in error. And the first column will be in error, right? So row 1 in error, column 1 in error, right? And that points to this bit needs to be corrected. If this bit is in error, what's the combination of row? Row will be 1. And which column? 3, right? Yeah. So if you have first row parity in error and third row parity in error, this should go and correct this bit. That's what we mean by there is a specific combination for every bit for which row and column will be in error.
Yeah, but my question is like, if you store exactly like the visualization, if you store only I plus j, correct? Because like it's like I and j here, but you said the storing data is I multiple j. So that's why I want to get the explanation why is
I times j,
yeah.
that's the number of parity bits, that's the overhead. So for every column you need a single bit parity. For every row you need a single bit parity. For every column, sorry, you are right, exactly. Yeah, this is I plus j, right? Is that what you are trying to say? Thank you so much. We have a correction. It's I plus j. You have I number of parity bits plus you have j number of parity bits. It's not I times j. I think that's what you are trying to say.
Because if
Yeah.
I multiple j will be whole.
Yeah. So this is a very important correction. Do you see the correction? It's I plus j, not I times j. Yeah, good spotting. Okay, so is it clear? Oh, okay, another question?
For the parity bit check at the bottom right.
At the bottom right, yes.
Is that the decision choice to parity check for the parity check for columns or rows?
Both, you have to do both.
Both?
Yeah, you have to do a parity check for all the rows, you have to do a parity check for all the columns, and then you can correct which bit needs to be corrected. Another question?
Yeah, so this system, it can detect that this error that happens in any bits?
Any bits, yeah. Any bit that is in error can be corrected.
Even like 0 bits are in error.
0 bits?
Like several bits are in error.
Oh, several. Now you're talking about multiple. Right? You're saying, yeah, you can detect 2-bit errors, we have just discussed.
So like if you have 4-bit error which happen in like row 1, column 1.
2-bit, you're talking about 2-bit?
Or 4 bits.
4 bits, yeah. Okay, so we have not discussed about 4. We say 2 bits we can detect, right? 2-bit error we can detect. How about 3 bits? We can detect any 3 bits, right? Right? Any 3 bits. How about 4 bits? That's the question he's asking. We didn't visit that. Can we detect 4 bits? Yes or no? Maybe, maybe not. Exactly, that's the correct. I can give you a particular pattern of 4-bit error that can be detected. For example, if you take 4 bits from the same row, right? Then that row will be in error, right? And 4 columns will be in error, right? No, sorry, that row will not be able to detect it. if 4 bits are in the same row, that row will not be able to detect it, but we'll have 4 columns that will detect it. Right? But I think he has a particular pattern in mind, so I will let him tell what's that 4-bit pattern he has in mind.
It's just like 4 bit in a square.
In a square, exactly. So let's draw it. It's a very good point. So I'll go here. So let's say this bit is in error, right? This bit is in error, this bit is in error, and this bit is in error. So the rows cannot detect it because 2 bits are in error. This row cannot detect it because 2 bits in error. This column cannot detect it because 2 bits in this column are in error. And this column cannot detect it because 2 bits in error. So I have 4-bit error pattern. In this case, will go undetected, let alone correction, right? That was your observation, right? Yeah, good.
Does this algo like always try to do the correction when there's like intersection?
Correction, only single bit you can correct.
Yeah, but like doesn't really know if it's like a single bit error or like a 3 bit error.
You do, sorry, could say it again?
Like for example, you have a 3-bit error in L shape. Right?
You're talking about the 2-dimensional?
Yeah, the matrix one.
2-dimensional?
Yeah.
Yeah, so you are saying there are 3-bit errors,
In an L shape.
L-shaped.
Yeah.
Okay,
And
let's see,
intersection-
let's create that error.
Yeah. So it's like you have
So 3-bit error, so for example, this one, and this one.
Yes.
Okay, so this will not be detected, this column, right?
Yes.
This row will be detected,
Yes.
right? So you can detect this 3-bit one, but you might try, yeah, so you can't correct, right? Because to correct a single bit error, you need a combination like this, a combination of row and column in error.
Yes.
So in this L shape that we talked about, there is one row that is in error, and oh, okay, you are right. So this column is in error, so you will correct this bit incorrectly.
Yeah, it's trying to correct the other bit.
Yes.
Which is
Yeah. So that's another problem.
So, based on my understanding, if somehow like 2 bits in the same row is somehow wrong, then that means that they can't detect.
Yeah, it will go undetected. We have already seen that, right, in single parity, that if an even number of bits are in error, a parity cannot detect it, whether it's a odd parity or even parity. We have already seen that. Yeah.
Because like it's like more combinations, so maybe like it gets confused which one to.
No, the parity doesn't switch. So let's say you are using odd parity. If a single bit changes, the parity will change from odd to even. If you have 3-bit in error, the parity will switch. If you have 5-bit error, parity will switch. The odd number of bits. But if even number of bits switch, then the parity will remain the same parity. And that's why it remains undetected. So 2-bit, 4-bit, 6-bit, 8-bit will go undetected. Okay. Any other questions on the parity system? But what we have uncovered, perhaps, through all these discussions, that not all bits can be corrected, detected. In some cases, the latest example that you have brought in is that you might incorrectly correct a single bit error, right? If there are 3-bit errors, right, you might incorrectly correct a single bit error. So that shows that error correction and detection is not that easy, right? So mostly we just focus on single bit errors. If there is a single bit error, can we detect it? And how to detect it? And if we want to correct a single bit error, what can we do? So this 2-dimensional parity is coming from the need to correct forward error correction. So we always talked about single bit detection, but here we can do single bit detection and correction. Yeah, but it's good that we are all aware of that not all bit patterns can be detected magically, right, by any error detection system. And that's why designing error detection and correction coding is a complex problem on its own in research. And even today, if you go to the journals, researchers are still publishing new papers on new error correction systems because they have higher capability. The probability that they can correct certain errors is higher than the previously. So research is continuously going on in this area. And here we are just looking at the very simple cases that is used in the internet today. So they are using this kind of parity systems. Okay, so I think with that, we can take a very brief break, 5 minutes break. And when we come back, we look at another kind of error correction, which is called cyclic redundancy check. So see you in 5 minutes.
I have some questions that you check. I think what I was wondering was that if for this example, if let's just say 4 bits are incorrect, is it the reason why it can't be detected is because there's just a lot of combinations where the row and the column can't detect
The row sees, oh, 2 bits are in error. So remember we just discussed that even number is zero, then you cannot detect. The 2 is even. This row will not detect it. The second row will not detect it. Column will not detect it. Other column will not detect it because 2 bits are in error. 2 is even.
So I think I'm more confused on why is there a reason maybe why is it when even bits are
In
so
error
like
then we can't detect it.
why can't we detect it?
Okay, so let's say you are using even parity, right? If I change 1 bit, it will change from even to odd. So you can detect it. But if you change 2 bits, it still remains even. That's why you cannot.
But what if maybe let's just say there are 2 ones, but they are changed to 0, then we can detect it, right? But still,
No, it remains even.
you mean I think I'll just
This
an
is one.
example. So let's say I change this to 1, 1, 2, 3, 4, 5, 6. Oh, it's still the same. Because I think I was thinking about that, I didn't really quite understand the rest of it. So I think I'm not too sure about when you're talking about, okay, if it's even parity, you can detect when the odd number of bits is flipped. And then
Flip it. So try it. Instead of 2, try 3. 3 is an odd number. Change 3 bits. It has switched from even to odd, so you'll be able to detect it.
So for this one, so if it's odd parity, then it can detect when the even number of bits have been flipped. If you're using an odd parity this time, then if an even number of bits have been flipped, then it can be detected.
No, you cannot detect it. If even number of bits are flipped, and the parity is not switched, whether you are using odd or even.
Oh, it can't be detected no matter what. Oh, okay. So I just. Also, you said some other things over here, like the even parity can detect when the odd is flipped. Odd parity can't be detected when the even is flipped.
Then I corrected it, remember?
Correct.
I corrected what I said.
Oh, talking about this one.
Yeah. That's why you were confused. Because I said it in the beginning and later I corrected it.
Oh, sure. So for this one, I'm just wondering why is it the number
There are I and there are J. So I plus J.
I plus j? But why do you have to get a 1?
Oh, there is another one here.
Oh, okay. So total around. So this is. So the numbers here and here plus 1.
Plus 1, you can use another one extra if you want. So you can say, okay, all this row, I will use another one if you want.
one is this one. Then the I is here and the J is here. Okay. Why do you put I times J?
Just incorrect, remember? I corrected myself.
Oh, because I thought you were talking about this, the number of bits total here.
No, not the total number of bits. I was talking about the number of parity bits.
Oh, okay. Right. So I think another question is, why can we detect odd number bits parity?
Why?
Why can we detect odd?
No, you have just done it, remember? If
Oh,
it's
okay.
odd, then it will switch the parity.
Oh, okay, for even parity.
Even for even, yeah, it will switch the parity.
Oh, okay, you will talk about even parity for most of the time.
Most of the time, yes, but that's also true for odd.
Oh, but it says if you switch even or odd, it can't be detected.
If you have odd number of errors in the system, then it will switch the parity.
Switch the parity?
Yeah. You have just done it, right? If you change 3 bits, it switches the parity.
Yeah, but then the error can be detected.
Detected, yes.
But if you're using odd parity, if you switch even or odd, then it can't be detected.
Now, if you switch odd number of bits, then the parity will be switched. Whether it's even parity or odd parity, doesn't matter. It will switch the parity, so you will be able to detect odd number of bits.
Oh, that's all right. Okay, sure. So it doesn't matter, but you can, if it's the parity switches, then you
Then you
will
can detect it, and you ask the question that this we only focused on even, but that's also true for odd.
So if you use an odd parity,
It's still the same. The conclusions that we have made is still the same. And that's why in this slide they just use even, because it doesn't matter.
Oh, okay. But if you use odd parity first,
It's still the same. These conclusions that we have made at the end still remains the same.
oh, because it can switch to even, and that's
Yeah.
where you find out.
Yeah.
Oh, right. Okay, sure.
I want to know if this is the two different version, or it can once I use the single parity first, and the second one I need to use the two-dimensional again.
Yeah. Actually, if you use two-dimensional,
Yeah.
you're also using the single parity bit, right?
Yeah.
Yeah.
So it's the advanced version of this one.
Yeah. Yeah.
And
It's an advanced version of this one. You are right. Yeah.
okay, so what about the angle, the last time, the
This one.
yes, I want to know what the meaning of this one.
What is the benefit of this one?
Yeah.
This is an additional parity bit that you can use if you want. So what you can do, you can say, I'm going to, for this column,
Yes.
I'm going to use another
So it's,
parity bit. That's what you can do if you want.
So it belongs to this one or not this one?
Yeah. It belongs to these parity bits. So you can say, I'm going to use another bit, which is a parity of these parity bits.
So it's the result of the row, not the
Row.
column.
Yeah. Or you can choose the columns, for example.
It's my decision.
Yeah.
Okay.
It's
Thank
your
you.
decision. Yeah. Okay, we are back. So we'll continue the error detection and correction, but this time we move to another kind of error detection technique called cyclic redundancy check. Okay, so before I go into the details of cyclic redundancy check, I just want to give you a very simple example in decimal system just to motivate you and intuitively convince you why this works, right? Otherwise, you spend a lot of time with the binary system, and it's hard to see the intuitive motivation behind CRC with the binary system. So I'll just use decimal. So let's say that you are trying to send a number 10, right? So I want to send this number 10, right? But if there's an error in the number, then I don't know if the number is in error or not. So cyclic redundancy check, I can say, okay, 3 is my generator for cyclic redundancy check. So you have a generator, and this generator is standardized, right? So every devices, they know this generator. So the sender knows this generator 3, and the receiver knows that the generator is 3. What you do with the generator? What's the job of the generator? So generator 3 is used to divide the number that you are trying to send, okay? And watch the remainder of the division process. So now you tell me, if I divide 10 by 3, what's the remainder? 1, exactly. It's not evenly divisible, right? 10 is not evenly divisible by 3. There is a remainder 1. What I do with the remainder 1, so before you transmit the number, you take the remainder off. Then instead of 10, you send 9, right? Now it sounds a bit funny, but don't worry about it. At the receiving end, then the received number is divided by this generator, 3. And if you divide it by 3, then you see that there is no problem. So that's the idea of generator, the number that you want to send, and then there is a remainder. If there is a remainder, take the remainder off so that the number is evenly divisible, and then send the number, which is always divisible by the generator. And at the receiving end, if it is not divisible, then we have a problem, because any single bit that flips will make the number not divisible. In the binary, we are going to see that. The only thing we need to fix is you wanted to send 10, and now you're not sending 10. So how does that work? So in binary, we'll see that we always send the data, but the number that we are talking about is not the original number. Okay, so it's longer than that. Okay, so we'll append some additional overhead bits. So it's the overhead bits that will be the remainder, and in the binary division process, we'll see that this concept we talked about, the remainder, division, taking the remainder off, these are all valid, and how this works. Okay, so that's just a preamble to this actual system. The way it works is this. So generator is 1 bit more than the overhead that you want to send. So in single bit parity, the overhead is 1 bit, right? You are sending 1 extra bit. Here, the number of extra bits we are sending is R bits, right? So R can be 3, R can be 4, R can be 33, 31, whatever, right? Like in two-dimensional parity, we have I plus j extra bits we are sending, right? Okay. So in CRC, you are sending R extra bit, let's say, right? So overhead is R extra bits. In that case, the generator has R plus 1 bits. They all come from this polynomial mathematics, right? So the mathematics is something that we are not going to explore, but we just gave you a link. If you're interested, you can go through the mathematics in WebCMS under this week 9. We have given you that link. Right, how can I explain without going to mathematics? So G is your generator, which is has 1 extra bit, right? So the way it works, in the beginning, so now I can go straight into the binary number system. So I just want to tell you one thing about the binary system, which is very useful for this, is addition and subtractions are identical, which is not true for decimal. So if I say take 1 away from 10, then it becomes 9. If I say add 1 to 10, it becomes 11. So 11 and 9 are not the same number. In binary, addition and subtraction in our case will be exactly the same. Why? because we are going to use exclusive OR. So if you add 1 plus 1, in exclusive OR it's 0, right? And 1 plus 0 is 1. And if you subtract 1 minus 1, again it's 0. If you subtract 1 minus 0, it's 1. So subtraction and addition will be considered the same in binary. We are going to use exclusive OR, right? So that's the first thing. Now, how does it work? So generator has 4 bits in this example, right? So the overhead will be 3 bits. Okay. And what is our data? So this is the data. 1, 2, 3, 4, 5, 6. It's a 6-bit data. In this particular example, we are interested in coding a 6-bit data with error detection code, so that we are going to transmit 6 plus 3, 9 bits, not 6 bits. 3 bits is the overhead. That 3 bits is the error detecting code. Like in IP, you have seen the checksum field is 16-bit, for example. It means that you have this extra 16-bit that you have to transmit on top of the data, right? So here, 6-bit is the data, and 3-bit is the extra bit. What we are going to see now, how do we calculate these 3 extra bits? So in the beginning, all these 3 extra bits are zeros. And later we'll see if we have any remainder or not. So 3 zeros means you are multiplying the data with 2 to power 3. If you shift the data to the left, you are multiplying it by 2. Shift one more time, you are multiplying by 2 to power 2. 4. Shift one more time, right? You are a computer scientist, so you know this shifting, right? You are putting 0 at the end. So if you put 1 0 at the end, you append, you are multiplying it by 2. Put 2 more zeros, the binary number, when you convert into decimal, you will see you have multiplied it by 4. So this is the logic, right? So you, in the beginning, just putting 3 zeros here, right? So this is your 3 zeros, right? So that multiplies it by 2 to the power 3. And then you are dividing it by this generator, right, which is 1001. But this is a binary division. What does it mean? You try to divide it. This is your division outcome, but we are not interested in this. We are not interested in the outcome of the division, but we are interested in the remainder, right? This is the remainder of your division. So we are interested. I will explain you the binary division later, but this is the remainder. Remainder means these 3 zeros will be replaced by this remainder here when you transmit. So when you transmit, it will be 0, 1, 1 instead of 0, 0, 0, because what you are doing, you are subtracting from this one, this remainder, because if you subtract, it's basically you are pasting this in here, because the subtraction and addition and the XOR. So if you XOR something with 0, you are just pasting that stream in there, right? Replacing the zeros, right? We have just seen that. So you are taking the remainder off from the number. It means that at the receiving end, when they do this division with this generator, remember the generator is known they should get all 0. They should not have any remainder because I have taken the remainder off. I divide, I find a remainder, I take the remainder off, I subtract the remainder from the number, and then I send the number. But the number that I'm dividing is not the original data. I shifted it by 3 zeros, right? So I'm still sending the data. In the previous example, instead of 10, I was sending 9. But this is not the case, right? I'm still sending the data. What is changing is the additional bits. That is the, so before I divided the original number, I multiplied the number with 2 to the power r. So it's a bigger number. So that shifts it. In binary, this becomes very useful for me because it's not a decimal number that I'm multiplying. It's the binary number I'm multiplying. So data is shifted to the left, and now I have nicely the additional 3 bits in this example, which needs to be calculated. And it's basically the remainder that I want to subtract from it so that at the other end it will be divisible. So in this example, what is the bit stream I'm going to transmit? So transmitted 1, 0. Data will not change. Remember, data should not change. This is your data. So I send the data and I send extra 3 bits. That 3 bits should be the remainder, right? Because if you take this 0, 1, 1 from this 0, 0, 0, it will become 0, 1, 1, right? Exclusive or subtraction addition is the same. That's my CRC, 3-bit CRC, right? So this is the number you transmit. If you divide this number by 1, 0, 0, 1, your remainder will be 0, 0, 0. If it is not, there is an error. Question?
Where should T come from?
Where does what come? D?
T.
D?
T code. The generate one.
G. Okay. Where did the G come from? So this is standardized, right? So there are generators for Ethernet, the generators for Wi-Fi. Okay, so the standards organizations, they publish this standard. So if you are a manufacturer, in your chip, you have to use that polynomial, that generator. It's a standard. You cannot just choose anything you like.
I have a question. I still don't really quite understand what you meant by shifting, and then
Shifting.
what you meant by replacing the 3 zeros with the.
Okay, shifting. So if this is your data, right? When I want to divide, I don't divide the data only, but I divide the data plus the CRC bit as all zeros. So what you are doing, you are multiplying the data with 2 to the power 3 in this case. That's what I mean by shifting. So the data is still there, but the data is a bigger data now. Data times 2 to power r. It's a bigger number that I want to divide, not the data itself. Yeah, so R is the CRC bit that you want to transmit. So you have made a decision that I will send 3 bits because you want to use this standard polynomial, standard generator, which is 4-bit. If it is 4-bit, the remainder will always be 3 bits.
Why do we need to shift the data?
Why do we need to shift the data?
Yes.
Okay, so in the beginning, the example I gave you, like you want to send a number 10, but your generator is 3, And if you divide the data itself, like which is 10, by 3, and the remainder is 1, and if you take the 1 off from the data, then your number becomes 9, and now you want to transmit 9. But you don't want to transmit 9. You should transmit 10, because the 10 is the number you wanted to transmit. You can't change the data, right? So we can't change the data. Data has to remain the same. So if you see what we have transmitted, which is at the bottom, I have just written. So this is what you have transmitted. So the data remains intact. Data remains intact. It's not changed. So that's why we shift the data with those 3 zeros, so that at the end we divide the bigger number to get those 3, which is the remainder. So you are dividing this number, okay, by G. And when you take the remainder, when you subtract the remainder from this one, these 3 zeros will be replaced by the CRC. You don't want your data bits to be replaced by anything. Data doesn't change, okay? That's why we created another number. Yeah. As I mentioned, in the beginning, the example I gave you is an intuitive example. However, it has this problem that the data was not sent, 10 and 9, right, the decimal number. But in binary, the actual implementation, this is what we do. So the data is preserved, and only the extra CRC bits are changed. Does that answer your question? Okay. You can check the mathematics behind it. You can read it, the polynomials and everything. And then hopefully that will give you more deeper understanding. But that's not within the scope. Yeah. Any other questions? Yeah.
What does the NG means, that N thing?
Yeah, NG means, again, that leads to the mathematics, and that's why I left it out. So, so this number here is divisible. So, you see, XOR is like subtracting, right? So, so this R is the remainder. So R is the remainder, right? If you take the R off, this is now divisible by G. So it is G times N. So it's divisible. It's a multiple of G. Yeah, that's why. N can be any number. Any other questions? So most important thing is not the maths behind it. The important thing here in this course is to understand the process, how CRC is working. So if I give you a data, if I give you a generator, can you tell me what CRC bits will be transmitted for this data? Can you calculate this? So you understand how they are doing it in the chip. So for example, you are using Wi-Fi mostly. So Wi-Fi has a polynomial generator, right? Usually 32 bits, so it has a 33-bit polynomial, which is a standard, right? And they are generating these CRCs all the time. And then at the receiver, they also know the generator, because that's for a particular version of the Wi-Fi. And then the remainder has to be 0. If it is not 0, then there is an error. Because if you change a single bit, so now I leave it to you, change a single bit and divide and see if you are getting the same remainder. The remainder will not be 0. Okay? Okay. Any other questions on CRC? You just need to find out that this division is binary. So you just take these 4 bits, you put it here, and then you see, you know, which bits you do the XOR, right? And then again you bring down the enough number of bits, 4 bits, copy it here. So you see, first you copy it here, second time you copy it here, third time you copy it here, right? And then 4th time you copy it here, and then it ends because you don't have any more bits, right? So you just need to trace this binary division, practice it a bit more to see that you can get the remainder. Okay, it's a binary division. We are just doing XOR. Right? Shall we leave it here and move on to medium access control? Because that's was something we wanted to finish today. Right. So, yeah, so you have already seen all of these things. You can, okay, maybe just we wrap it up, because we have seen so many different kinds of error detection and correction techniques by now. Here is a quiz to wrap it up. So the question is saying that you have these checksums, remember checksums, TCP and IP. Okay. And then 2-dimensional parity, which we have seen today. And then this CRC we have just seen now, right? So these 3 things, the question is saying, can these schemes correct any bit errors? Can they correct? The focus is on correction, right? So in the answer, you have 3 things. The first one is for checksum, the second one is for 2-dimensional parity, and the third one and the answer should be either yes or no, because the question is on correction. Can it correct anything? So the first one is yes, no, no. It means the checksum can correct something. 2-dimensional parity cannot correct anything, and no for CRC cannot. Is that true? How many of you think is true? No one. Okay, good. B, checksum cannot correct anything. 2-dimensional parity can correct something, and CRC can correct something. Is that true? Anyone? Okay, again, no one says correct. Okay, how about C? Checksum cannot correct anything. 2-dimensional can correct something, and CRC cannot correct anything. Is that true? Now I can see quite a few hands up. Okay? Maybe this is true, because we know in checksum, we have already discussed it cannot correct anything. But in 2-dimensional parity, remember, we stressed it many times that it's the correction that's important, and it can correct single-bit errors. So the answer is yes.
When did we respectively correct any bit errors?
First one is checksum, the second one is 2-dimensional parity, and the third one is CRC. That's a respective.
Do they mean like you can it's guaranteed that you can correct all the bit errors?
Not all the bit errors, any. So in this case, a single bit error correction is good enough. Yeah. Okay, so you got the correct answer. Good. However, this quiz also highlights that only the 2-dimensional parity is capable of forward error correction. Even the CRC is not capable, right? It can only detect. So CRC is heavily used in Wi-Fi and in many other protocols. But again, this is just for detection. If you want to correct, then it's more complicated. So there are some complicated CRCs, but we are not going to study that. Okay, so we move on to multiple access protocols. So the thing is, the point-to-point is possible, but mostly in many networks, the resources are shared, especially in wireless, right? So point-to-point means if I want this host to communicate with this host, I have a link. If I want to communicate, I have another link, another link, another link. So point-to-point, there is no problem, but the problem is that you need lots of wire, right? And if you go into wireless, you need lots of frequencies, a lot of resources. So as a result, what we want to do is to share the channel among many devices, right? That's the fundamental thing in computer networking. So that's the medium access control, and this is done in the data link layer. So all the chips you see, the Wi-Fi chips you have, they implement this kind of medium access control. So to control who should send when, because when something is shared, the problem is if you do not coordinate this, the use of the shared resources, there will be collision. Collision means in computer networking, the signals will collide with each other, and whoever is the receiver will have a hard time to understand who is saying what, because the signals are corrupted, right? So this is a fundamental problem, and medium access control means there has to be some control so that the medium, the broadcast medium, so we'll focus on the second part, not the point to point, but we'll focus on this one. We need some kind of control so that these situations can be avoided, the collisions can be avoided, or collisions should be detected so that we can retransmit. Okay, heavily used in wireless, 4G, 5G satellite, these are all wireless, but in some old-fashioned Ethernet, they also use this one, right? But these old-fashioned Ethernet are still there in many places. Okay, so I will quickly go into, okay, before I go into that, this is the ideal, some ideal properties that we would like to have in the medium access control protocols. I'm not saying that we have them in every practical systems, but this is like a design goal. So the first one is saying that if there is only one node in the system, there is no competition, for example, right? Then this node should be able to use the full capacity of the channel, right? Because there is no one else. Second, that if there are multiple nodes, m nodes in the system want to transmit, then on average, everyone should get R is the capacity data rate of the channel, R over M, right? They should be able to share it equally. It means that the overhead of this medium access control should be minimal, because if a lot of capacity is lost just to maintain this control, then it's not very ideal, right? So we still want to use this, and it should be fair. Okay. The third one is saying decentralized. Now, decentralized is important because in computer networking, centralized control has lots of problems, right? Because then you need another device or another entity to become the centralized controller, and if this one fails, then the whole system fails, right? So you want to be distributed. We are all sharing this space. For example, in this one, we are sharing the air space, right? So when I talk, you are not talking, because if you start to talk when I am talking, then it's not good for anyone. Nobody can actually understand what's going on, because our speech will interfere with each other in your ear, and then you will have problem. But we do not have a central controller. I don't bring another controller with me saying that he will decide who will talk first. It's just a common sense. We are just using our common sense. So it's decentralized, right? We have some etiquette that when one person talks, we should not talk, right? And this is a decentralized control. We want something like this in our computer networking, right? We want decentralized. We don't want any clock synchronization. Clock synchronization means if I have m devices, they all need to follow the same clock. It's very difficult, okay? Because you know that every device comes with its own clock and own crystal and own counting, right? And it's always different, right? It's always different. If you look at your watch, not the mobile phone, because mobile phone is synchronized to the base station. But if you have those old-fashioned wristwatch, check the time, you will see the time is always different, down to the millisecond, right? Sometimes even in seconds, they are different. So synchronizing requires a lot of infrastructure. For example, all the mobile phones are synchronized because we have a mobile tower somewhere, right? So we don't want this kind of synchronization, and we want it to be simple to implement, right? So these are our like wish list, if you like. Right, with that wish list in mind, I just go to the taxonomy, right? Because there are so many different kinds of medium access control protocols, it's good to have a high-level taxonomy to see what are the types available. So there are two main types. One is partitioning and one is random, right? Partitioning is deterministic and the random is non-deterministic. So it's worth just to write that here. So it's a deterministic access to the channel. By now you are familiar with my handwriting, so it should be fine. Non-deterministic, so I use my voice as well, so you can read it later. Right, so random, and so these are the two fundamentals. So what is partitioning and what is random? Partitioning means in advance you partition the resources in a way so there is no possibility of collision, right? And I'll show you two fundamental way to partition a channel. And then the later one is random. That is, you do not partition in the beginning, but you try to randomly access it whenever you need it, right? You think it's more efficient, so in certain scenarios it is more efficient, but in some other cases the random is not very efficient, and that's why they use deterministic, right? So both are in use today. Okay, so let's go to the partitioning and what are the two fundamental ways of achieving partitioning, right? So two fundamental ways is time and frequency. So time is TDMA, time division multiple access, and frequency is frequency division multiple access. So in this picture you see there's a 6-node local area network. So there are 6 nodes competing for the same resources at the data link layer, right? And we are using time to partition the channel. So we are saying that I will divide the access to the channel into some slots, right? So first slot will be dedicated to the first node, second slot will be dedicated to the second node, and so on, and the 6th slot will be dedicated to the 6th node. So if it is your time to transmit, then only you can transmit. In other slots, you are not allowed to transmit. This way, if you partition, and these slots are coming back, so you will always have your time coming back. Everyone is given a fixed time, and after that they have to leave it. So your time will always come back, right? But there is a specific time for you. So in this case, in TDMA, there is no way there will be a collision. You agree with that? There is no way that two people will transmit at the same time. So there is no collision, no possibility of collision. You agree with that? So TDMA can completely avoid collision, right? So this is heavily used in many systems. Time division, multiple access can, with 100% guarantee, avoid collisions in multiple access systems. Now, who can give me one example from a real life of TDMA? It should not be computer networking. I'm not interested in computer networking now. I'm interested in social life, physical life, our daily routine life when we go outside. There are so many examples where we have to share resources, right, with many people, with multiple entities. Who can give me one example where time division multiplexing is used? Just to reinforce the understanding of TDMA, rather than me coming from me, I want it to come from you. I will assist you, but you have to volunteer. Think. In real life, you're going out there and you're sharing some resources. Who can give me an example? What office?
The microwave in your office.
Microwave
Machine in your office, right?
in your office.
Yeah, it's shit.
Microwave means the cooking thing.
Yeah, the cooking.
Yeah. And can you tell me what's the scenario we are looking at?
And
Who is coming to use it?
yeah, at a lunch break,
Yeah.
all of the staff's gonna be using maybe the same microwave, and they have to take turn to use this, because it's just the same machine.
Yeah. But do you allocate that Mahbub will use the first 30 seconds, and after 30 seconds Mahbub has to leave it? The second 30 second is allocated to you. Do we create the access like that, or everybody queues in front of the microwave and they take a turn from the queue?
Yeah, you don't really need to use that sometimes.
Yeah. So this time division multiplexing is saying that this time, okay, we have an example.
Classroom,
Classroom, okay, then go on.
like everyone, like this room, is booked, 10 to 12 every time, no pollution, no class.
Yeah, it's a very good example. Okay, I didn't think it that way. I thought that within the classroom you were going to say. Okay, that's a clever one. So they are saying that the classroom is a common resource in the university, but if you look at the schedule, they say that 9 to 11 is Comp 3331. So during this time, nobody can come to this classroom and give another lecture, right? But from 11 to 1, it may be some another Comp 4336, and at that time, it has to be Comp 336. That way, we do not have any collision in this room. So it's the scheduling of resources, right? So meeting rooms, they are scheduled. So if you go there in the schedule, then you can see who will be using at what time. Very good example. Okay, I don't need any more example. So you can see that one. The only thing I will highlight here is that you can see some empty slots at the bottom, right? So the empty slots is because that node, when it's time to transmit, he or she has nothing to send. So today, if I was sick, for example, and I didn't come to this lecture, I don't think they would allow another lecturer to use it for another subject, because that lecturer is not available, right? He is available for another time. So what will happen? This room will not be used. So that's what's happening here. So that's the drawback of TDMA, time division multiplexes. So remember, one of the goal was to good utilization, but here it will go empty if somebody is not using it, because the time slots are strictly dedicated to people. But at least you understood how TDMA works. Every method in this world will have disadvantages. Don't worry too much. Don't get hung up on every disadvantage, right? But do you understand how TDMA works? That's the most important thing. Okay? Everyone, no questions on TDMA? Very good. So I switch to the second, not second most, the other most widely used fundamental method of partitioning the channel and medium access control. That's called frequency division multiplexes. So you can see here, at the same time, multiple users can use this channel. However, it's divided not in time, it's divided in space, or if you like, in frequency, in communications or wireless digital communication, because frequency is a resource. So in the example of this room, you can say we can divide the room into 4 corners. 4 lecturers come in 4 corners, and there are soundproof things, so they do not interfere with each other. So in wireless communication or wireline communication or any digital signal processing, if you are using 2 different frequencies, although they arrive at the same time, our ear or our instruments, the Wi-Fi chips, they can easily decode them if they are 2 different frequencies, thanks to a famous algorithm called Fourier transform. So in frequency domain, once we convert the time domain information in frequency domain, if they have 2 different frequencies, they appear quite different in the frequency domain. So there is no problem of decoding them. There is no collision if they are using two different frequencies, right? A good example is a language. Language is kind of a frequency. So if there is an English coming and a Chinese coming at the same time, and I'm just focusing on the English, I have no problem. No problem, because I'm focusing on the English, right? So Chinese is like a noise, right? So similar thing here, frequency. That's why they are sending at the same time. So if I allocate them different frequencies, then I can achieve multiple access to the same channel, because they will get different frequencies and 100% guaranteed that they will not collide. So there is no collision, right? Is that clear? Who can tell me the main disadvantage, one disadvantage of FDM? Limited resource. Can you elaborate a little bit more? What do you mean by limited resource?
Like if the frequency of book, so you cannot have the new one, the new channel for any other.
You can have more users by giving everyone less frequency band. But you were right, limited. You said something interesting. Maybe someone wants to elaborate on that. Lower speed. This is correct. Why? Why lower speed? Sorry?
The shared online.
Shared, yeah. Yeah, okay, I take it. So what she is saying is that you can see the whole channel is not allocated to a single user. The channel is divided into different bands, and each one is allowed to use only a portion of that channel. It means even if no one else is transmitting, you are not allowed to transmit at the full capacity of the channel, right? So if I divide the room into 4 corners, I will have a very limited space to talk to my students, even if no one is using the other corners, right? So that's the major disadvantage. In time division multiplexing, when it's my time, I use the entire bandwidth of the channel at an extremely high data rate. Is that clear? This is the fundamental difference between frequency division multiplexing and time division multiplexing. In frequency division multiplexing, the advantage is at the same time. So I can send any time I have the data ready. No latency. So latency is another huge performance metric for computer networking that I do not have to tell you, right? Because you have already gone through your midterm, and the questions were the latency, right? How many RTT is needed to download a web page? What is it? It's about latency, the performance. Latency, delay is a huge problem, right? So in slot, once I finish my slot, I have to wait for everyone else to use the channel before the channel will be given to me. So there is a delay. Here, anytime I have data, I can transmit. It may be low speed, but there is no delay, right? That's the advantage of FDM. The disadvantage is when it's my time, I get a small portion of the capacity. Question?
So like it's all the frequencies being like transmitted, but the one with the higher frequency is more listened to compared to the others.
Higher frequency what?
Oh, like for example, there's like